Imagine for a moment that you're standing in your backyard on a clear night, looking up at the stars. Each pinprick of light represents a sun, many of them far more massive and brilliant than our own. But here's what will absolutely transform how you see that view forever.
Every single star you can see with your naked eye, every constellation that has guided human navigation for millennia, every celestial landmark that has inspired countless generations of dreamers and poets, represents less than 1/10 billionth of what actually exists in the observable universe. Let that sink in for a moment. Everything your eyes can take in during a lifetime of stargazing is such an infinitely small fraction of reality that it's almost mathematically insignificant. And yet, even this incomprehensibly vast observable universe might itself be just a tiny bubble floating in something even more enormous than we can possibly conceive. Welcome to a journey that will take us from the familiar boundaries of our solar neighborhood to the very edge of everything we can theoretically observe. We'll discover why there's a limit to how far we can see, not because our telescopes aren't powerful enough, but because of the fundamental nature of space, time, and light itself. We'll explore how the universe's own expansion creates a cosmic horizon beyond which no information can ever reach us, no matter how long we wait or how advanced our technology becomes. But first, let's establish something that might surprise you. When astronomers talk about the observable universe, they're not talking about everything that exists, they're talking about everything we could possibly see, even with perfect instruments and unlimited time. The distinction is crucial because it reveals one of the most profound limitations built into the very fabric of reality itself. The observable universe has a radius of approximately 46.12 billion light-years in every direction from Earth. That means it's a sphere roughly 93 billion light-years across, containing everything from which light has had enough time to reach us since the beginning of time itself. But here's where it gets fascinating and slightly mind-bending. The universe is only about 13.8 billion years old. So how can we see objects that are 46 billion light-years away? The answer lies in one of the most elegant and mysterious features of our cosmos. Space itself is expanding. While light from distant galaxies has been traveling toward us for billions of years, those galaxies have been carried farther and farther away by the expansion of space itself. It's like watching a runner on a treadmill that's moving backward faster than they can run forward. The light eventually reaches us, but by the time it arrives, its source is much, much farther away than when the journey began. This creates something called the particle horizon, the boundary of our observable universe. Beyond this horizon lies what we might call the unobservable universe, regions of space that exist but remain forever hidden from our view. No telescope will ever peer beyond this boundary. No signal will ever cross it. No information will ever bridge this cosmic divide. It's not a limitation of technology or human ingenuity. It's a fundamental feature of reality itself, written into the laws of physics that govern everything. But let's start our journey small and work our way outward, building our cosmic perspective one scale at a time. Because understanding the true size of the observable universe requires us to first grasp just how empty and vast space is, even in our own celestial neighborhood. Picture Earth as a marble sitting on a football field. On this scale, the moon would be a peppercorn about 7.5 yards away. Already, the distance has become difficult to visualize, but we're just getting started. The sun, our local star that seems so dominant in our sky, would be a beach ball sitting about 2.5 miles away from our marble Earth. And the nearest star beyond the sun, it would be another beach ball located roughly 13,000 miles away. This is the scale of just our immediate stellar neighborhood. And already, we're dealing with distances that challenge human comprehension. But this is nothing compared to what lies ahead. Our entire solar system, including the distant orbit of Neptune and the scattered objects of the Kuiper Belt, would fit within a circle about 10 miles across on our football field scale. But our galaxy, the Milky Way, contains roughly 400 billion stars, each separated by these mind-numbing distances. If our solar system is 10 miles across, then our galaxy would span the entire continental United States. And this is just one galaxy among countless others scattered throughout the observable universe. The Milky Way belongs to a small group of galaxies called the Local Group, which includes our neighbor Andromeda, a few dozen smaller galaxies, and a handful of dwarf companions. This entire local group spans about 10 million light-years across, but even this collection of galaxies is just a tiny cluster in a much larger structure. The local group is part of something called the Virgo supercluster, a vast collection of galaxy groups and clusters that spans roughly 110 million light-years across and contains thousands of galaxies. When you look up at the night sky, every star you see belongs to our single galaxy, but our galaxy is just one of thousands in this local supercluster. But we're still not even close to grasping the full scale of what we can observe. The Virgo supercluster is itself part of an even larger structure called the Laniakea supercluster, which contains roughly 100,000 galaxies spread across 520 million light-years. The name Laniakea comes from Hawaiian words meaning immeasurable heaven, and it's a fitting description for a structure so vast that light takes over 500 million years to cross it. And yet, Laniakea is just one of millions of similar superclusters scattered throughout the observable universe like islands in an infinite cosmic ocean. Between these superclusters lie vast regions of nearly empty space called cosmic voids. These voids are so large that entire superclusters could fit inside them with room to spare. Some voids are over 1 billion light-years across, containing almost nothing but the occasional lonely galaxy drifting through the cosmic darkness. This creates what cosmologists call the cosmic web, a stunning large-scale structure where matter is arranged in filaments and sheets separated by enormous voids. If you could somehow step outside the observable universe and look at it from a distance, it would resemble a vast three-dimensional spiderweb with bright filaments of galaxies separated by dark empty spaces. The cosmic web stretches across the entire observable universe, and every galaxy, every star, every planet, every living thing exists somewhere within this magnificent structure. We are part of this web, tiny inhabitants of a small planet orbiting an ordinary star in an unremarkable galaxy that sits along one of these cosmic filaments. But here's what makes this truly extraordinary. The cosmic web isn't random. Its structure was determined by tiny quantum fluctuations that existed when the universe was smaller than an atom. These microscopic variations in density grew over billions of years, shaped by gravity and the expansion of space itself, until they became the vast architecture we observe today. Every galaxy cluster, every void, every filament in the cosmic web can trace its origins back to quantum uncertainties that existed in the first fraction of a second after the Big Bang. The universe has grown from quantum foam to cosmic web, from the smallest possible scales to the largest structures we can observe. And as we map more and more of the observable universe, we discover that this cosmic web extends as far as we can see in every direction. No matter which way we point our telescopes, we find more galaxies, more clusters, more superclusters arranged in the same web-like pattern. The observable universe appears to be filled with structure on every scale we can measure. But there's something even more remarkable about the cosmic web that speaks to the fundamental nature of reality itself. The visible matter that makes up galaxies and stars accounts for less than 5% of everything in the observable universe. The rest is composed of mysterious substances we call dark matter and dark energy, invisible components that reveal themselves only through their gravitational effects on the matter we can see. Dark matter makes up about 27% of the observable universe. It doesn't emit, absorb, or reflect light, but its gravity shapes the cosmic web, providing the scaffolding around which visible matter clusters. Without dark matter, galaxies couldn't have formed, stars couldn't have ignited, and the cosmic web itself couldn't exist. Dark energy comprises the remaining 68% of everything, and it's even more mysterious. This invisible force is driving the accelerating expansion of space itself, pushing galaxies apart and stretching the cosmic web ever larger. Dark energy is why distant galaxies are receding from us faster and faster, and why the observable universe has a finite size despite the universe's ongoing expansion. This means that the vast majority of the observable universe consists of things we cannot see, touch, or directly detect. We are like explorers mapping an invisible continent, inferring the presence of mountains and valleys only by watching how rivers flow around them. The cosmic web we observe is merely the visible tip of a much larger hidden architecture that shapes everything around us. But even these staggering scales pale in comparison to what we discover when we consider the observable universe as a whole. Recent measurements suggest that the observable universe contains at least 2 trillion galaxies, each containing hundreds of billions of stars. That's more stars than there are grains of sand on every beach on Earth, multiplied by every beach that has ever existed throughout our planet's history. Let me put this in perspective for you. If you counted 1 star every second without stopping, it would take you longer than the current age of the universe to count all the stars in just one large galaxy. To count all the stars in the observable universe at this rate would require more time than has elapsed since the Big Bang, multiplied by trillions upon trillions. And yet, despite containing this incomprehensible number of stars and galaxies, the observable universe remains mostly empty space. If we distributed all the matter in the observable universe evenly throughout its volume, we would end up with roughly 6 protons per cubic meter. That's emptier than the best vacuum we can create in laboratories on Earth. This emptiness isn't a flaw in cosmic design, it's a fundamental feature that makes complexity possible. Without vast spaces between stars, planetary orbits would be unstable. Without enormous distances between galaxies, gravitational interactions would prevent the stable structures necessary for life. The universe's emptiness is what allows islands of matter to exist as oases of complexity in an ocean of space. As we push our observations to greater and greater distances, we're not just looking farther into space, we're looking backward through time itself. Light travels at a finite speed, roughly 300 million meters per second, which means that distant objects appear to us as they were when their light began its journey to Earth. When we observe a galaxy 1 billion light-years away, we're seeing it as it existed 1 billion years ago. The light carrying that image has been traveling through space for 1 billion years, crossing vast distances while the universe itself expanded around it. By the time that ancient light reaches our telescopes, the galaxy that emitted it may have evolved, changed, or even been destroyed by cosmic forces we cannot yet observe. This creates a remarkable consequence. As we peer deeper into space, we're witnessing the universe's history unfolding before us. The most distant galaxies we can observe appear young, chaotic, and fundamentally different from the mature spiral and elliptical galaxies we see nearby. We're watching cosmic evolution in reverse, seeing the universe grow younger and more primordial as we look farther away. The most distant objects we can currently observe are galaxies that formed when the universe was less than 1 billion years old. These ancient systems appear as small, irregular collections of stars, frantically forming new suns at rates hundreds of times faster than galaxies today. They give us glimpses of the cosmic dawn, when the first stellar nurseries were igniting throughout the expanding universe. But even these incredibly distant galaxies aren't the farthest things we can observe. The most distant light we can detect comes from the cosmic microwave background, radiation left over from when the universe first became transparent, roughly 380,000 years after the Big Bang. This ancient light fills the entire sky with a faint glow that's invisible to our eyes, but detectable by sensitive radio telescopes. It represents the afterglow of creation itself, the moment when the universe cooled enough for the first atoms to form and light to travel freely through space for the first time. The cosmic microwave background marks the edge of our observable universe, not because nothing exists beyond it, but because we cannot see anything that happened before the universe became transparent. It's like trying to peer through fog so thick that no light can penetrate. The cosmic microwave background is our cosmic fog, the fundamental limit to how far back in time we can observe. This creates one of the most profound realizations about the observable universe. We live at the center of our observable sphere, not because we occupy a special place in the cosmos, but because we can only see objects from which light has had time to reach us. Every observer in the universe sits at the center of their own observable sphere, each with a slightly different view of cosmic history.
An observer in a galaxy 10 billion light-years away would see their own observable universe overlapping with ours, but extending in directions we can never explore.
They might observe galaxies that remain forever hidden from our view. While some of the galaxies we can see lie beyond their cosmic horizon, This raises a fascinating question about the nature of existence itself. If there are regions of the universe that can never send us information, that we can never observe or influence, do they truly exist in any meaningful sense? Or does existence require the possibility of observation and interaction? Modern physics suggests that these unobservable regions are indeed real, filled with galaxies, stars, and possibly even civilizations that are simply too far away for their light to reach us. The universe beyond our cosmic horizon continues the same cosmic web, the same processes of stellar birth and death, the same dance of matter and energy that we observe within our visible sphere. But we can never confirm this directly. The unobservable universe remains forever theoretical, inferred from our understanding of cosmic uniformity and the laws of physics, but never directly witnessed. It exists in a realm beyond empirical science, where mathematics and philosophy converge to grapple with questions of existence and reality. The expansion of space itself ensures that our observable universe is constantly changing. Every second, light from more distant regions crosses our cosmic horizon and becomes observable for the first time. We are constantly receiving new information from the early universe, watching the cosmic story unfold as ancient light finally completes its billion-year journey to our telescopes. But paradoxically, the accelerating expansion driven by dark energy means that many galaxies we can currently observe are moving away from us so rapidly that we will eventually lose sight of them. Their light will become so stretched by cosmic expansion that it fades beyond detection. Future astronomers will inhabit a lonelier universe, with fewer visible galaxies and less evidence of cosmic history. In the far future, if current theories are correct, the observable universe will contain only our local group of galaxies. The rest of the cosmic web will have expanded beyond our horizon, leaving future civilizations with no way to discover the Big Bang, cosmic expansion, or the rich tapestry of cosmic evolution that we are privileged to observe today. This temporal window makes our current era special in cosmic history. We live at a unique moment when the universe is old enough for complex structures to have formed, but young enough that we can still observe the evidence of cosmic origins. We are cosmic archaeologists, working within a limited time frame, racing to understand our origins before the expanding universe erases the evidence. The observable universe thus represents not just a spatial boundary, but a temporal one as well. It defines not only how far we can see, but how much cosmic history remains accessible to scientific investigation. Every observation we make, every discovery we achieve, adds another piece to a cosmic puzzle that becomes more difficult to solve with each passing billion years. As we contemplate these vast scales, something profound begins to emerge about our place in this cosmic theatre. The observable universe isn't just a collection of distant objects scattered through space. It's a living, breathing entity that connects us to every other point of light in the cosmic web, through the fundamental forces that govern reality itself. Consider this remarkable fact. Every atom in your body was forged in the nuclear furnaces of ancient stars that lived and died billions of years before our solar system even existed. The calcium in your bones, the iron in your blood, the oxygen you breathe at this very moment. All of these elements were created in stellar cores and scattered across the cosmos by supernovae that lit up galaxies when the universe was young. You are not separate from the observable universe. You are made of it. You are the cosmos, becoming aware of itself, a temporary arrangement of stellar debris that has somehow achieved the extraordinary feat of consciousness. Through your eyes, the universe observes its own immensity. Through your mind, it contemplates its own origins and destiny. This connection runs deeper than mere poetic metaphor. The laws of physics that govern the behavior of galaxies billions of light years away are the same laws that govern the electrical impulses in your brain. As you process these words, the gravitational forces that hold galaxy clusters together operate on the same principles that keep your feet planted on the ground. The electromagnetic radiation that carries information across cosmic distances is the same force that allows your neurons to communicate with each other. But here's where the scale of the observable universe becomes truly mind-altering. If we could somehow shrink the entire observable universe down to the size of Earth, Our own galaxy would be smaller than a single cell in your body. Our solar system would be invisible to the most powerful microscopes. And Earth itself would be so inconceivably tiny that it would exist on scales smaller than we have words to describe. Yet, on this infinite decimal speck, in a universe so vast that our entire galaxy is essentially a point, complexity has reached levels that boggle the mind. Life has emerged from lifeless matter. Consciousness has arisen from unconscious atoms. Intelligence has developed to the point where it can contemplate its own cosmic context and ask questions about the nature of existence itself. This creates one of the most beautiful paradoxes in all of cosmology. We are simultaneously insignificant and extraordinary. Insignificant because we occupy such an infinite, dissimally small portion of space and time. Extraordinary because, despite our cosmic smallness, we have managed to map the observable universe, understand its history, and predict its future. The observable universe reveals itself to us through light, that fundamental messenger that connects every corner of cosmic space. But light does more than just carry information. It defines the very structure of space-time itself, creating the boundaries of what we can observe and establishing the cosmic horizons that limit our knowledge. Einstein showed us that space and time are woven together into a single fabric, and the speed of light represents the maximum rate at which information can travel through this cosmic tapestry. This speed limit isn't just a property of light itself, it's a fundamental feature of reality that governs how cause and effect propagate through the universe. Every photon that reaches your eye from a distant star has been traveling at exactly this cosmic speed limit for years, decades, centuries, or even billions of years. These ancient messengers carry with them the history of their journey, encoded in wavelength that tell us about the temperature, composition, and motion of objects scattered throughout the observable universe. When astronomers analyze the light from distant galaxies, they're not just seeing pretty pictures, they're decoding messages that have traveled across unimaginable distances, carrying information about stellar births and deaths, the formation of heavy elements, the merger of galaxies, and the evolution of cosmic structure itself. The existence of dark energy means that we live during a special epoch in cosmic history. We inhabit a universe old enough for complex structures to have formed, but young enough that we can still observe evidence of cosmic origins and evolution. Future civilizations will face a lonelier cosmos, with fewer visible galaxies and less accessible information about cosmic history. This temporal window makes every observation precious, every measurement valuable. We are cosmic archaeologists, working within a limited time frame, racing to understand the universe before the expanding cosmos erases the evidence. Each photon we collect from distant galaxies represents irreplaceable information about cosmic evolution, stellar formation, and the fundamental forces that shape reality. The observable universe thus serves as both our laboratory and our library, containing within its boundaries all the information we can ever hope to gather about the nature of existence itself. Every star we observe, every galaxy we catalogue, every measurement we make, adds another piece to the grand puzzle of cosmic understanding. But perhaps most remarkably, the observable universe continues to reveal new mysteries, even as we solve old ones. The more we learn about cosmic structure and evolution, the more we discover how much we still don't understand. Dark matter and darkening remain largely mysterious despite decades of intensive research. The ultimate fate of the universe remains uncertain, dependent on the long-term behavior of forces we can barely detect. Recent observations have revealed that the cosmic web extends to the very edges of our observable sphere, suggesting that the same large-scale structure continues beyond our cosmic horizon. This implies that the unobservable universe contains countless more galaxies, clusters, and superclusters arranged in the same magnificent pattern we see within our visible sphere. The total amount of matter and energy in the unobservable universe could dwarf what we can see by factors of billions, trillions, or even infinite amounts. We may inhabit just one small bubble in an infinite cosmic ocean, forever isolated from the vast majority of reality by the fundamental limits imposed by the speed of light and the expansion of space. This possibility transforms our understanding of cosmic significance. If the observable universe represents just a tiny fraction of total reality, then our already minuscule place in the cosmos becomes even more infinitesimal. Yet this cosmic humility brings with it a profound sense of wonder and connection to something far greater than ourselves. We are participants in a cosmic story that began nearly 14 billion years ago and will continue for trillions of years into the future. Our brief moment of consciousness represents just an instant in this vast temporal expanse, but it is an instant filled with the extraordinary privilege of awareness, curiosity, and understanding. The observable universe serves as our window into this grander narrative, offering glimpses of cosmic birth, evolution, and destiny. Through careful observation and measurement, we've managed to reconstruct the history of everything we can see, from the quantum fluctuations that seeded cosmic structure to the stellar processes that forged the elements of life. This scientific understanding connects us to every photon of starlight, every distant galaxy, every cosmic process unfolding across the observable universe. Ultimately, the observable universe is more than just a collection of stars, galaxies, and dark matter. It is a mirror, reflecting back to us our own origins and our extraordinary capacity to comprehend the cosmos. It reminds us that we are made of the universe itself, its atoms, its energy, its history, and that through consciousness, the cosmos has become aware of itself. We are both insignificant and extraordinary. Insignificant because we occupy such a tiny portion of space and time. Extraordinary because despite our cosmic smallness, we can observe, understand, and marvel at the universe. Through our eyes, the universe sees itself. Through our minds, it contemplates its own origins and destiny. And in that realization lies one of the deepest truths of all. We are the universe, alive, aware, and capable of asking the questions that stretch across space and time itself. We are not isolated observers looking at a foreign cosmos. We are integral participants in the ongoing cosmic story, temporary arrangements of matter and energy that have achieved the remarkable feat of cosmic self-awareness. As you drift deeper into contemplation tonight, remember that you carry within yourself the history of the observable universe. The atoms in your body have journeyed across billions of light years and billions of years to become part of you. You are a living, breathing piece of cosmic evolution, a temporary but magnificent expression of the universe's endless creativity and complexity. The observable universe holds within its boundaries not just matter and energy, but time itself in its most tangible form. Every moment of cosmic history since the universe became transparent is preserved somewhere in the light still traveling toward us. Ancient supernovae that exploded billions of years ago are still announcing their deaths to telescopes across the cosmos. Stellar nurseries that form the first heavy elements continue broadcasting their creative work through radiation that has crossed unimaginable distances to reach our instruments today. This creates a profound realization about the nature of information and existence. The observable universe serves as a vast library where every significant event leaves its signature in the electromagnetic spectrum. The birth of stars writes itself in ultraviolet light. The death of massive suns inscribes itself in gamma rays and neutrinos. The collision of neutron stars etches its story in gravitational waves that ripple through space-time itself. We are surrounded by messages from across the cosmic web, each photon carrying news of distant worlds and ancient events. Some of this light began its journey when Earth was still a molten ball of rock. Other radiation started traveling toward us before our solar system even existed, carrying information from an era when the Milky Way was still forming from smaller galactic fragments. But here's what makes this truly extraordinary. As we develop more sensitive instruments and more sophisticated analysis techniques, we're not just seeing farther into space, we're reading the cosmic story with greater and greater detail, discovering subtleties in the universal narrative that were invisible to previous generations of astronomers. Modern space telescopes can detect the chemical signatures of individual elements in stellar atmospheres located billions of light years away. We can measure the rotation rates of galaxies so distant that their light has been traveling since the universe was a fraction of its current age. We can even observe the shadows cast by cosmic structures on the cosmic microwave background, revealing details about the universe when it was only a few 100,000 years old. These capabilities allow us to witness cosmic evolution as it unfolds across the observable universe. We can watch galaxies merge and separate, see black holes consume stellar material, observe the formation of planetary systems around distant stars. The cosmos reveals itself as a dynamic, ever-changing theater, where creation and destruction dance together on scales that dwarf human comprehension. Yet for all its vastness, the observable universe operates according to the same fundamental laws that govern processes here on Earth. The fusion reactions powering stars in distant galaxies follow identical principles to those we study in laboratories. The gravitational interactions shaping galaxy clusters obey the same mathematical relationships that describe falling objects in Earth's gravity. This universality of physical law creates a deep connection between the most distant objects we can observe and the immediate reality we experience. The light from a quasar billions of light years away interacts with atoms in our telescopes, according to precisely the same quantum mechanical rules that govern the behavior of electrons in our own bodies. The elements forged in the cores of ancient supernovae and scattered across the cosmic web eventually found their way into the molecular clouds that gave birth to our solar system. The gold in your jewelry, the iron in your blood, the calcium in your bones, all of these heavy elements were created through stellar nucleosynthesis in massive stars that lived and died long before Earth existed. This means you are directly connected to the most distant reaches of the observable universe through the very atoms that comprise your being. You are not merely an observer of cosmic evolution, you are a product of it, a temporary but magnificent arrangement of stellar debris that has achieved the extraordinary ability to contemplate its own cosmic origins. The realization becomes even more profound when we consider that consciousness itself might be one of the rarest and most significant phenomena in the observable universe. Despite containing trillions of galaxies and countless billions of stars, we have yet to detect any definitive signs of life beyond Earth, let alone intelligence capable of cosmic contemplation. This apparent rarity of consciousness makes your existence and indeed the existence of every thinking being incredibly precious in cosmic terms. You represent billions of years of stellar evolution, planetary formation, and biological development, culminating in awareness capable of understanding the universe itself. Through your consciousness, the cosmos achieves something remarkable: self-reflection. The universe becomes aware of its own immensity, contemplates its own history, and ponders its own future. You are the observable universe looking at itself, thinking about itself, marveling at its own complexity and beauty. This perspective transforms how we understand our place in the cosmic hierarchy. While we may be infinitesimally small in spatial terms, we represent something genuinely extraordinary in terms of complexity and capability. The human brain contains roughly as many neurons as there are stars in our galaxy, creating a network of connections that rivals the cosmic web itself in its intricate organization. The thoughts you're having right now as you contemplate these cosmic scales involve electrical and chemical processes of staggering complexity. Information flows through your neural networks at speeds that allow you to process concepts spanning billions of light years and billions of years. Your mind serves as a kind of miniature universe, complete with its own networks, patterns, and emergent properties. But the observable universe continues to challenge and expand our understanding in ways that keep revealing new layers of mystery. Recent discoveries have shown that the cosmic web exhibits properties we never anticipated. Dark matter appears to interact with itself in subtle ways we're only beginning to detect. Dark energy might not be constant, but could be evolving over cosmic time, potentially altering the ultimate fate of everything we can observe. Some of the most distant galaxies we can now detect appear to have formed much earlier and grown much larger than our models predicted. They challenge our understanding of how quickly structure can assemble in the early universe and force us to reconsider the processes that governed cosmic evolution during its first billion years. These ongoing discoveries remind us that the observable universe remains largely mysterious despite centuries of intensive study. We have mapped its large-scale structure, measured its age and composition, and traced its history back to within moments of the Big Bang. Yet fundamental questions about its nature and destiny remain unanswered. Why does the universe appear to be fine-tuned for the existence of complex structures like galaxies, stars, and life? What determines the values of fundamental constants that make chemistry and biology possible? Is our observable universe unique? Or does it represent just one possibility among countless others in some larger multiverse? These questions push us toward the boundaries of scientific understanding, where observation meets theory and mathematics